You're welcome. Let us look at today how we can get the relationship between CP and CV, where this CP and CV are what we call the molar heat capacities. CP is actually what we call molar heat capacity at constant pressure. Therefore, this P stands for pressure, and CV stands for molar heat capacity at constant volume. We want to see the relationship between the two terms. CP, sometimes we call them the principal molar heat capacities. Principal molar heat capacity at a constant pressure, and this is the principal molar heat capacity at a constant volume. Now, how do we define the two? CP is actually the amount of heat or the quantity of heat that is required to raise the temperature of 1 mole of a gas by 1 degree Celsius or 1 Kelvin. And then that is at a constant what? Pressure, on condition that the pressure is constant. When we come to molar heat capacity at a constant volume, is actually the amount of heat required to raise the temperature of 1 mole of a gas by 1 Kelvin or 1 degree Celsius at a constant volume. So that is the definition of the two. So what actually differentiates the two definitions here, we say at the end at a constant pressure. At the end here we say at a constant volume. So let us see how the two are related. Now, consider first of all 1 mole of a gas, and this gas is heated through 1 Kelvin at constant pressure. At constant pressure. Therefore, we shall have that from the first law of thermodynamics. So the heat that is being supplied, is at a constant pressure. Goes to do two things: to increase its internal energy, that is change in U, plus do the external work. So that is from the first law of thermodynamics. The heat that is being supplied into the system of a gas does two things. One, it goes to do or increase its internal energy, that is both potential and then kinetic. And then secondly, it must do the external work, like expansion of the gas. Now in this case, but we know that change in QP, the heat that is being supplied at a constant pressure, it means the number of moles times the specific heat capacity at constant pressure times the change in temperature. So therefore, we shall have that N, instead I will now put it here, NCP, change in T is equal to change in U plus change in W. But of course, we shall have that, in this case, we should have that N, but of course, we know that N is 1, this is number of moles. The number of moles is 1, that's why we say 1 mole of a gas. Then change in T is also equal to 1, because we are racing through 1 Kelvin. So therefore, we shall have that this is 1, this is 1. Therefore, we shall have CP equal to change in U plus change in W. So here, that is what we have for this case. But then, of course, if it is at a constant pressure, then it is pressure that is being constant, that means the volume is changing, and so I can express this in terms of volume. We actually derived it. So, but then we know that change in W is P change in volume. So therefore, we shall have that Cp becomes change in U plus P change in V. That is what we have for this case. So you will see that, but this volume is changing from V1 to V2. So I can change this and say Cp is equal to change in U plus, this becomes P, open a bracket, V2 minus V1. This is change in V. A change in V would be the volume V2 minus V1. So from this case, I can call this equation 1. Let me call it equation 1. We are also going to consider one mole of a gas being heated through 1 Kelvin, okay, at this time at constant volume. At this time we have the volume is constant. So still from the first law of thermodynamics, we shall have that change in Q. The heat supplied at a constant volume goes to do two things still: increase the internal energy and do the external work. And so, but this one, but change in Q, V is actually NCV, and then times the change in temperature. Times the change in temperature. That's that. So we will have that, and we need to see that change in W, actually work done is P, change in V. But then, in this case, we are dealing at a constant volume. So meaning a change in V is 0. So since change in V equal to 0, that means the work done is 0. So there is no external work done in that case. So we can come and put it here. We shall have NCV, change in T becomes change in U plus 0. That one I cannot write it. So it remains like that. So since this is N is 1, use 1 mole, and then change in T is also 1 Kelvin. So it means, it implies that CV becomes equal to a change in what? In U. I can put this as equation 2. So here, instead of change in U, I am going to replace it CV here in equation 1. So I will say substituting for change in U in equation 1, we shall have that Cp equal to Cv. Now this change in U is equal to Cv plus P, open a bracket, V2 minus V1. So we are going to, because in our expression we don't have this V2, V1, even P, at the end of it all will disappear. So we have to express this. So I can ideally have Cp equal to Cv plus, this is PV2 minus PV1 when I open this bracket. But we also know that from gas laws, from an ideal gas equation, we shall have that PV equal to nRT. But for this case, I have two volumes, V1 initially and then V2. That is initially PV equal to 1 when the temperature is T. And then, we shall have that PV2, this one here, is nRT. But now this T to be plus a change in T. Like that. Because now this is the temperature initially when the volume is V1. This now becomes the temperature because we are raising the temperature of this gas through 1 Kelvin. And this change in T is actually 1. So, but then I can even put it here, but change in T is 1 Kelvin. So I can put it and say PV2 becomes nRT plus 1. So if we replace it here, therefore CP becomes CV plus P2. PV2 is here, is nR, open a bracket, T plus 1. And then here minus PV1 is actually nRT. I can open this bracket. So I'll have CP becomes CV plus nRT and then plus nR, okay, minus nRT. So you see this nRT and nRT will cancel themselves. So I'll have that CP equal to CV plus nR. But of course also n is equal to 1. So this implies that CP is actually CV plus R. So I can rewrite this as CP minus CV equal to R, where this R is what we call the molar heat capacity. Not the molar heat capacity, it's actually the molar gas constant, and its value is known as 8.31. Now, it means that for any gas, its CP is always more than the CV. So, such that when you subtract CV from CP, you get R, which is the molar gas constant. The reason being, at constant pressure, the heat that is being supplied goes to do two things. It increases the internal energy of the gas and also does the external work. But at constant volume, the heat that is being supplied only goes to increase the internal energy of the gas. And there is no work done externally, either for expansion of the gas, because the volume remains constant. So it is always that the heat that is being supplied, the mole at constant pressure would be higher than the one supplied at a constant volume. So, and that is the relationship between CP and CV. Thank you very much. Keep following.